Good morning. I can see we have some survivors from yesterday after party. All right. I hope you had a good 2 days of the conference, and I hope I'm not going to ruin the beginning of the third day for you. My name is Michal. Friends call me Wheels of Fury, and they have good reasons for that. This picture from International Space Station shows both my home right now. I come from northern Poland, and now I live in southern Sweden when I work for Triton 37. We're a consulting company. We have offices in 4 cities in Sweden. We really like to share our knowledge, so we're quite active in conferences, and we also organize our conference, LeadSpeak. Today we're going to talk about computers and how do they work, or actually how things work under what we're used to do in our everyday work. So where the idea for the talk come from? I was talking with younger colleagues from my office and realized the people who come from maybe from a different system education than me don't really go to like university, just for example learn programming by themselves or go to some 2 years programming course. They never really are forced to familiarize them what's running on the bottom of our high-level programming languages. And it's maybe not that important, you don't really need it in your everyday life, but it's awfully interesting, so figure out I'm going to make this talk internally. And it was very well received, so I figured, well, why not do it somewhere externally? And quite often when you do programming these days, we either use like NPM or NuGet. We don't really have to, know a lot of stuff. We can use a lot of packages, and there's nothing wrong about it. It makes us productive. It makes us deliver stuff very quickly. But sometimes stuff like this happens, and it makes us doubt if the way we're doing is this right, and maybe we're losing the contact what's happening below the code. If you're not familiar with this situation, leftbot was like 7 lines of code packet manager that was shifting text, and half of the internet was depending on that. So when the author pulled off the package from the NPM, half of the open source project broke that day. It was a wonderful day in the open source world. So these days we, like most of us, probably program with like high-level programming languages like C#, Java, Python, JS, and they don't really like run their code directly on the CPU. They're run in some form of sandbox, virtual machine, CLR, you name it. Usually the code is compiled into some intermediate way that's then JIT compiled to native code and run on the operating system. And it has some benefits. So we have automated memory management. We don't have to like allocate memory, free it. It's relatively easy to do cross-platform software on that because we just need different interpretation of that virtual machine on different CPUs or architectures and so on. But the underlying code can stay mostly the same. If you ever tried this practically, the world is not so nice and beautiful, but it's much easier if you have to develop for every platform directly, natively. And your code can't really violate memory, or you shouldn't really say never. So let's say it can easily violate memory, but if you've been long enough, you've seen stuff happening. Or if you mess with people like Trey Hunt, like everything's possible. But let's look what's happening a bit closer to the metal. And languages like C and C++, which probably some of you used to program or did something in school at least, and there have some benefits too. They gives you usually a bit better performance if written properly. You have also much better control what's happening with memory, and in some situation it's needed. But also we have to do a lot of additional work to make stuff happen. So for example, concatenation strings in C is quite an annoying job. because strings are arrays of characters or bytes ended with 0. And if you want to allocate those, if you want to concatenate strings, you have to calculate how long there are, allocate new piece of memory for that stuff, and copy first string at the beginning and second at some buffered place. You can put it out, and then you have to free that memory, because if you don't free, it's not gonna get freed automatically, and you're gonna start leaking memory. But there are some places where it's still very usable, and like C and C++ is very like C++ mostly is extensively used in like 3D graphics for games. When you do some physics simulations and models, quite often machine learning models. We have like nice APIs in Python or C# when you use like CNTK, or when you use TensorFlow. But all the underlying code is written in C++, and all that calculation is done natively on a machine with C++. High-frequency trading is another example, because for them it's very important to have very low latency, and if a garbage collector turns on in some moment when it's not available, the latency like goes to the roof. So they like to control when they garbage collect or when they free memory and so on. And also in embedded system where you have quite limited to the memory, although it's less and less true, because now embedded system can even run JavaScript, so we live in happy times. And also, it's not like we stuck in the old ways with C and C++, because there's a lot of new developments in area for languages that are compiled to native stuff. So languages like new standards of C++ bring a lot of new features. We get actually garbage collector, we have smart pointers. Also languages like Rust and Go have a lot of very nice features that can be also compiled to native. But again, that's not the code that's directly run on your CPUs. So today we're going to talk about assembly for IA32 architecture, so the Intel architecture. And I'm going to limit myself to the 32-bit architecture, because it's just simple to show. Has less register, has a simpler instruction set, but a lot of this stuff apply and works on today like 64 extension to this architecture, because it's been just extended. There's a ton of new features, and there's a lot of things happening, but the basics are very much the same. So let's look at a simple line of assembly code. That's how it looks usually. We have some instruction and some arguments to this instruction. So this instruction add the number 1337 to register EAX. So what's EAX? What are registers? So I'm going to sidetrack right now to a couple things that happen around CPU or directly in the CPU. So we have things like registers. Registers are small like cells of memory directly on the CPU, or not technically in the CPU, but in the same box. So the way you look outside, it's inside the CPU. But it's not particularly part of the processing unit, it's just registers. So in 32-bit architectures, registers have 32 bits, so 4 bytes. So you can fit integer into there. In the extension to the 64-bit extension to the architecture, they have 64 bits, so you can fit long into there. And the other thing that we're going to talk about today is stack. Stack is a piece of memory that's somewhat usual in the RAM, in the random access memory, but it's a special kind of memory. And you can put you can have like 2 operations in a stack. You can put stuff on, and you can pop stuff from the stack. So you kind of layer things up on the top, and you can take things from the top. We're going to talk a bit more in a moment. There are also things that are like not relevant to these talks, but also happening in our CPU. So we have general RAM. It's not really in the CPU. It's next to it. It's connected to a bus, and it's not like. For us, like when we see like a disk is a slow memory, RAM seems very fast memory, But for the CPU, RAM is very slow memory, so it also has a few levels of cache. And basically, the first level of cache is usually very small, and it's very fast, and we have up to 5 levels, which the 5th is probably the biggest and the slowest. And this is like some sort of extension to the RAM, where CPUs keep the data that we'll need quite often. So if you look at what's the fastest to slower, we're looking first registers, then cache, then it will be RAM, and the stack is a packet of RAM, and then we're looking at like slow memories like disks or external storage. So registers in 32-bit Intel architecture, we have 8 of them. 6 of them are general purpose registers, so you can technically use them for wherever you want. There are 2 registers used for special things. One is for a stack, so we point where exactly at the stack we are. So where's the top of the stack? And base pointer is the pointer that shows base memory for a function we are. So basically where in memory starts current function we're running right now. So it's useful also for returning from that function and so on. As you can see, one also interesting register is ESI. That's usually used as an instruction pointer. So because instructions are also stored somewhere in the memory, and you have to know at which instruction you're currently at when you're like stepping your program. Those 4 registers, EAX, EBX, E6, EDX, you can see you can also address the lower 16 bits of that, and also the lower 8 bits. This comes as a kind of legacy from the 8 and 16-bit architecture, but it's quite sometimes useful. If you really want to optimize your code and don't want to use all 4 bytes of the register, you can just use the lower 4 bytes or just lower 1 byte and pack data more tightly. Right, so let's back to our instruction and what does it mean. Or actually, this is again not something our computer literally understands. Our computer understands something like that. Those are actually the in a hexadecimal representation how this instruction would be seen by processor and operated. So how do I know that? Back when I was at the beginning of university, on my first course of computer architecture, the first task we had was like still quite early era of internet in Poland. So we have to go to Intel website and order the physical books, and they came after 4 weeks from United States from Intel for free. You could order it from them. Now you can just download PDF, but back then they were sending the physical books. When you look at one of the pages, there's like basically hundreds of pages, and 2 first books are just instruction set where all the instructions available for processor are listed and how to actually use them. So what I want to do is add to EAX register immediate value, so just integer value, and that's the opcode 05, and then ID is integer of size a double word, so it's 4 bits. You can see other sizes, like there is B, which is like byte, which is 1 byte, word, which is 2 bytes, and double word, which is 4 bytes. So you can see, as I told you, you can address those 8, 16, and 32 bits parts of that register, as I saw in the image, and you can just add this data to just like lower parts of the register. Fun fact: this thing's probably gonna get optimized to this opcode, so it's gonna be add AX and 2 bytes, because we only use our number fits easily into 2 bytes. So probably your compiler actually down optimizes it to use only those 2 bytes. But just for brevity, I'm using this. As you can see, also 1337 in hexadecimal is 539, but those bits are flipped. First bits are the lowest meaning, and then is the highest, which is feels a bit weird, but that's like there are two ways of sending bits. There's big endian and little endian, and I think that's little endian. I don't exactly remember, doesn't matter, but basically the way the bits are sent, you first see the list important bits, yes, and then the most important bits. So yeah, that's the opcode, then like the number of operation you saw in the book, and that's the parameter we were sending in through. So let's look at simple function in assembly code. This function will add two numbers, and this is complete code for adding two numbers. It's like complete program in assembly code. So first we have some declaration. .386 notifies instruction sets for like 386 CPU. I picked that because this was the first one processor with like 32-bit instruction set. So it has all we need for that. With later processors, you also had like more extended instruction set. So you had stuff like MMX and operation to do like operations to act on array data and so on. And then we have the code segment. So you can also have a data segment apart from code segment. When you declare like sort of like local variables, you can declare what's in the memory. So you can basically put in data, something like constants in programs we write in high-level programming. And code segments has like opening and ending. We declare some things here, but not gonna dig into it right now. It's not very important. And that's the actual function code. We have a start of the function and end. And we're gonna dig and debug this function, but first let's talk about some other things. Let's talk about stack again. I also already mentioned that there are like two main operations on the stack. You can push things and add at the top of the stacks, and you can pop and remove from the top of the stacks. And we have some base address where the stack starts in the memory, and usually because we're operating on 32 bits, so we add whole 4 bytes of data. So we increment address by 4 every time we add something. So we increment the pointer by 4 and put the data here. You can increment it by 2 or by 1 or by 3 if you're crazy, because with we have very good control. We can access every bit of memory. But usually you just don't want to it. You just want to access the whole bits of data. But yeah, you can do other things. Just the thing is with x86 architecture, the stack is some weird anti-gravitational stack, and we start from the top and build things on the bottom of it. So when you push stuff on the stack, let's say push integer number 3 on the stack, we actually decrease the address because that's how it works in x3. And if you push another things on the stack, we again decrease it by 8. Oops. Yeah. And if you want something pop, you have to pop it to some other place. So you can pop to AAX register, or you can pop in some place in your RAM memory. And then you have to increment the stack pointer. Here's I'm using the like ESP, the stack pointer we mentioned previously, and this is the EAP, which is the instruction pointer we talked previously. And so this number, after we pop it, it logs somewhere in the EAX register, and that's like the part of stack that interests us, underlined with the red squiggly line, but the memory is still there. The thing is, like when you program in a low level, you can never expect one that's in the place of memory because there can be trash from your previous operations. So quite often when you like declare new variables in low-level languages, you have to like set it to zero because you have never sure what's there in this memory. So that's another funny thing about low-level programming that we tend to forget. And there's something like calling conventions, so the way you call functions. So the CDECL convention that's used in the like Windows-based systems or like DOS, but that's what we get from those systems. And the way it works, if you have like 2 arguments in the function, or 3 arguments for the function, you pass them from the back. So if you have 3 arguments, you pass first, third, then second, then first. So if you have 2, you first press second argument, and then the first. It doesn't really matter if you call function like sum, but it matters if you call function like if you divide something, then the order of operations makes, like the order of arguments makes sense. But that's how it thinks. And then when you call function, you get something like a return address. So there's going to be information for function where it should return the stack pointer when it's finished their operation. So now we can get back to our functions. So we call the function sum, so we add the return address of the stack. Now we push EBP, which is like base pointer, because we want to save wherever the base pointer for previous function that called our function. So we store it on the stack, so we don't forget. And now we set as a base pointer the stack pointer, because that's the start of operation for our current functions. That's the piece of memory that our function will operate. And we don't want it to look at the piece of memories that belongs to other functions, because we start violate their memory. And then we have to do it all manually and make sure we just keep to our memory. And now I simulated here a processor, so we have a register, so we can follow what's happening, which is basically stepping like in Visual Studio. So now we're moving to EAX, the second argument from this function, which is 3. And I'm moving to ECX, which is another register, the first argument. And the way I pick those registers is a bit like, I just picked them because I picked them like that. Usually it doesn't matter. They're called general purpose registers because you can use them for some stuff. But it's sometimes good to remember that, for example, all of the operations, by default, if you don't, if they don't have any like output value, the default value is that they will return the value to EAX register. So you have to keep that in mind and maybe not keep their information that you want to keep for later. But here we're doing just openly. We're just adding, we're adding EAX and ECX, and it's going to be added to the first register, so it's EAX. So now we have sum in our ADRX. Okay, now we're coming to the part of action that we want to actually exit the function. So we're getting back EBP, so that if we return to the next function, the function that called this function, it's going to get their base pointer back. And we're going return, which basically jump us to the return address. So now I'm going to run some demos. I prepared some actual code written in assembly and other things. So it's going to start with first one. I'm going to do a startup project. So I wrote a small math library, and it has 2 functions. One is dumb multiply, and second is a smart multiply. What dumb multiply does, it's, let's say we want to multiply 3 by 7. So I'm going to loop 3 times and add 7 to some register. So basically we're going to loop 3 times and add the number 3 times, which kind of works like a multiply, but it's like very stupid way to do it. The reason I'm doing is just show you how loops works in assembly. This code is this library I called from C code. So this C code is like very simple. Just no, it's actually same example, 7 by 3. So cool. I'm just gonna run debugger. That's sort of expected. And all right, I'm gonna now step into, and now we're jumping from C code to assembly code. And we're doing the same things I described. So we're popping some things, moving it, and now we're moving the arguments to the registers. So let's do this. And also initializing accumulator, so the register will keep their result. As I told you, we just put 0 in there just in case, because we have no idea what to store in there. Actually, Visual Studio shows that there's some like 116.42240. So this is like some trash memory that was used by some previous program or wherever. So that's cool. And now we have something called start here. That's just a label. And then we're gonna just jump to this label at the length of this block of code. And GNZ is an instruction that will jump to the label if value in the EBX register is different than 0. So GNZ means jump if not 0. And there's a lot of like conventions in the assembly, so you can just know that it means that the 0 cannot be in the EBX register. So we're gonna use EBX as our like iterator or like counter of the loop. And in every step of the loop, I'll add to our accumulator the second argument, and we'll decrease the first argument, which will gonna be our counter. And this will do as long as the EBX equals 0. So let's step up through it like a few times. You can see we're going 7 times across the loop. Nothing unexpected, and at some point we'll probably get out of it. So as you can see, goto is how our processor acts. That's like the default act of operation. It doesn't mean you should write goto, because compiler does it, so we don't have to. Cool. And now I'm gonna return this EDX, which was our accumulated value, which is 21. So that's the right answer for like multiplying 3 by 7. But we have to move it back to EAX, because EAX is default register for returning stuff. So as you can see, there's like a thread here, common, that EAX is quite often used as a default register for things. All right, so let's get out of the functions. We'll do a popping, and we're returning, and we're back in the C code. And to step out one step more, and we can see that dump prod is 21. So that's expected value. That's what we wanted to see. All right, let's step in now in the smart prod, which is like another function on the road, which is using emul operation, which is basically integer multiplying. So, do I have a breakpoint set up here? I do. So we can step in. We do again those whole things we do at the beginning of the thing. We're taking arguments, and we just do emul and have a result in EAX and the return. So each line of assembly code is like one cycle of CPU. So our dump prod took around like 4 lines, times 7 times. It's probably around 28 cycles or something like that. And our smart multiply did it with 1 cycle, because it's just like one operation built in the CPU. It's implemented with some like gates and things like that on the electrical level, and it's much more faster than what we're doing in this semi-programmatic way. All right, so we get the result, and yeah, doesn't really matter. So that's the C code. So we can call the assembly from C code, and Sometimes when you're writing your C code and it's not fast enough, you want to more control, you can write pieces of your code assembly. It's all cool. But let's try to go like one layer up. I packed it all in the library. So this is the same code that's just like packed in the library. And I have a C# code that's gonna try to use this library. So what we're gonna do is gonna run C# code that's gonna call the C code that's gonna call the assembly code. And the way you do it with C# is something called platform invoke, pinvoke. So I'm importing the DLL that I built here within this project. We're using this DCL calling convention. You have to like declare it, how the library, what kind of convention it expects, and this is just gonna do something like that. We're gonna calculate a times x plus b function. So the C code in the native library is basically we use multiply from assembly code, and we return this plus b calculated in C code, and our that's our library. Cool. Let's see how it works. So I'll get to the program CS. I have a breakpoint set up, so let's just start it. So 3 times 5 plus 7, that's gonna be 15, should be 22. So let's see if it does expect result. Yeah, it is 22. It's probably the window gonna disappear, but I can start without debugging. And yes, we have 22. It's barely visible here, so we have to believe it, but that's well. Yeah, but probably quite a lot of us write today's JavaScript. So let's maybe write some JavaScript that will call C# code, that will call C code, that will call assembly, eventually that. How about that? So to do this, I made a small web server with Nancy, which is like a small .NET framework for making web services. So that's what I do. I basically start service. I set up localhost, and I have one module which takes just the index and has some API. And I wrote some JavaScript code. That's probably terribly bad JavaScript code because it's not what I do on my everyday basis. Let's see the code here. Source. Show me the source. I want to see visual stuff. Yeah. So basically, I just AJAX to the API I'm running in the server, and this server calls the native library, and this native library, you know the drill. So let's just run it and see if it does what we want. All right. Let's just refresh it. All right, so 3 times 4 on 12 plus 5. Yes, let's try something else. So it does work, but you may not believe me that we're running this assembly code. So let's do something else. Let's mess with assembly code to show that it's actually the same code we're running. I'm gonna stop this whole app, go to the library that we're running, go to the assembly code, and we're just gonna add 1000 to the result, just for the shit and giggles. All right, we need to rebuild this library because assembly needs to reassemble, let's call it like that. It's gonna take a minute. Now we can listen to Venkat while it's happening. Okay, I think it succeeded. So let's hope for the best. All right, the server is running. I'm I'm gonna refresh it. Yes. So yeah. This shows that the stuff we're doing, we may be living in a happy JavaScript or C# or Java or wherever is your poison language word, but it's all built upon layers, and we're kind of standing on the shoulders of giant who started like programming computer with bits, and they came up with idea that's, you know, doing it with bits is stupid. Let's come with some language that's going to be super cool for that, and they came up with assembly. And the next generation people figure out that assembly is a bit harsh, so maybe let's find something that's going to be better. And over that we're going to, and we're in the world of JavaScript, so not sure if we didn't do something wrong on the way. But I think that's the end of my demo. So let's get back to slides. I have a couple of more. I went really quick this morning, so we'll probably have a time for more coffee. Cool, slides. All good, all good. So Intel is not the only architecture we talk. It's just the most common for us. What's the characteristic for Intel architecture has a lot of instructions, but just small amount to register. Like in the 32 bits, we have like 8 registers. I think 64 extensions has like 128 registers or something like that. So we have like much more available, but still it's quite limited amount. But numbers of instructions is like, it's very, very big. So it's very like every instruction is optimized in that way. But there are like architectural like RISC, which means reduced instruction set computer architecture, something like that. And they don't have like just few amounts of instructions that are very basic, but have like a lot of registers that do very specific things, and it's like very convention based. So that's also very interesting. And we're going to have big endian, little endian, 16 bytes, 24 bytes. So it's all interesting, but like each of those architecture will have their own assembly code, and you just have to do other things. So like leaving a layer up when we have actually running our code on virtual machines is quite convenient on an everyday basis. If you'd like to dig more into this stuff, this is a fantastic book. The Charles Petzold starts with like just flashlight and explaining binary array, and goes all the way up to building like array gates, NAND gates, and so on, up to building the transistors, and you know, pretty much building operation system from scratch. It's a really cool book. So thank you for coming. I put some resources on my blog on this fix, and I'm going to keep it on the screen. So if you have any question, I can take them now. Yes?
How did the C++ code know about the assembly code? How was it referred to?
All right, I can actually get back to code and show this. Stop that. Let's go to the first. So, so that's the like definition of the function, and I have a file here that's C. It calls it, but I also have a header file that's thing, and it displays those functions, and it kind of shows that, like for H file, it see those in the H file that this kind of function exists. So it's kind of a bit like defining interface in a high-level programming. And then what linker does, which is like a program that connects files during compiler, you pass to the linker all the files, and the linker gets all the files as an input, analyze what's the name of the functions and everything in those files, and then link them to those kind of interfaces that you declare in a header file. So that's what gets connected during linking files of compiling.
Do you write the linker file?
No, linker is kind of like so when you would compile manually, you probably would be like, you would like GCC and pass all the files as the input files, and linker is just one of the steps of the compiling. So just put those things together. So I think it's I linking statically here. Yeah. Yeah. So, yeah. So the function are named the same as the assembly file. They just use the underscore notation, but just the same file. So when you do a compiler step, you pass as an input value all the files that's important for this thing, and this will do like parsing of the files and just find the functions that will like connect them. It's, I guess if I remember correctly, there are some problems. You have to have functions named the same in different files. Then you start running into problems, and that's where like namespace come into these languages. But back then you have to like make sure how your naming convention works properly and so on. I don't see the whole stage, so it's everybody. If you have a question, just wave intensively. All right, yeah.
It's the question about the assembly.
Yeah?
This is an abstraction of the operations, physical operations in the processor.
Mm-hmm.
Can you execute the same assembly, or you need to compile for a certain processor architecture, but can you use the same assembly code over many architectures, let's say Intel?
Yeah. So now this is like very specific assembly to like Intel architecture. If you look, for example, like Commodore 64, the assembly is going to be different, and so on. And this is not that much of an abstraction. It's just like kind of a nicer way to putting it. So when we get back to the
So you just have words instead
of those binary numbers. So just like for more readability. So what happens? Few slides back. No. So basically, this is like directly getting translated, and so that's basically what this computer runs, and this is just for readability.
Can you write in somewhere, someplace, some ID, something? Can you write directly
In zeros and ones and so on, or hex? Yes. So actually, if you, I'm not sure if it's gonna. I don't have it prepared, but if you like actually take like the object file, which is like output of compilation, and you're gonna see the hex view, you're gonna see actually a lot of those opcodes that you can recognize. So this you can what you could technically do, you could just write zeros, ones, or like hex values in Notepad, save it as an object file, and also like act as a compiled file, and you can just reference this directly. So this is like directly the code that's being sent to the CPU and run. Yeah. It would be very tedious, but definitely possible. Yeah. Yes? I looked it into bits. I think it's a very interesting topic. And yeah, but I don't have any smart to say about it. It's just, I started looking into it. Yes?
You can actually make a program that is changing itself.
Yes.
You can write into your own bytes.
Yes, you can write into your own bytes of places where you store instructions, so you can change the instructions during running the actual instructions, yes. We're sort of in the danger zone, but it is possible. I've never done that, no. All right. Please remember to vote. If you have more questions during the day, I'll be the whole day here. And enjoy the rest of the day. Thank you.